Chapter 3, Instrument Transformers. Instrument transformers are a special type of transformers used for the measurement of voltage and current. As the name suggests, these transformers are used in conjunction with the relevant instruments such as ammeters, voltmeters, wattmeters, energy meters, as well as protection relays. Such transformers are of two types. There are current transformers that are used when the magnitude of the AC current exceeds the safe value of the current measuring devices or the instruments, and they are designed for working at various voltage levels. Potential transformers or voltage transformers are used for a similar purpose, and that is when the voltage of the AC circuit exceeds 750 volts, as it is not possible to provide adequate insulation on measuring instruments for that voltage level. Then the potential or voltage transformer is introduced into the circuit so that the voltage to the instrument can be at a safe level. And just as there are various voltage ratings on a current transformer, there's also various voltage ratings on a potential transformer. These are examples of CTs or current transformers that are found in a power transformer. They are known as donut CTs for their similar look to a donut. The picture on the right is not a CT, but a typical transformer bushing, which would be mounted through the center of a donut CT. The secondary winding is wrapped concentrically around a toroid, which is usually made up of laminated iron or steel. The primary is a single conductor, usually a bushing mounted through the center of the toroid. The donut fits over the primary conductor, which constitutes one primary turn. The secondary is wound around the toroid core, which is usually made up of laminated iron that concentrates the magnetic flux and forces it through the secondary turns. Some donut CTs come with the primary conductor incorporated in the CT, as you see here. If the toroid is wound with 240 secondary turns, then the ratio of the CT is 240 to 1, or 1200 to 5 amp. The 5 amp designates the continuous rating of the secondary winding and is normally 5 amps in North America and 1 amp or 0.5 amp in many other parts of the world. This type of donut CT is almost or most commonly used in circuit breakers and transformers. The CT fits into the bushing turret, and the bushing fits through the center of the donut CTs. Up to 4 CTs of this type can be installed around each bushing. Instrument transformers are used for the following reasons. 1, to insulate high voltage circuits from the measuring circuit in order to protect the measuring instrument from damage. 2, to make it possible to measure high voltage with low range voltmeters and high current with low range ammeters. These instrument transformers are also used in controlling and protecting circuits to operate relays, circuit breakers, etc. Voltage and current phasors can be summed easily on the secondary circuits of these transformers without causing short circuits, as would happen if you were trying to, say, sum 2 currents on the primary side. So that a lot of times when you want to sum various currents, say, in a circuit and measure them, you can do this quite safely on the secondaries of current transformers. Now let's take a look at current transformer ratios. In an ideal transformer with a simple load on the secondary and an AC voltage on the primary, the secondary voltage V subscript S is determined by the turns ratio such that Vs all over Vp is equal to the same ratio as the turns of the secondary of the transformer over the turns of the primary of that transformer. The secondary current, Is, is determined by the turns ratio such that Ip times Np is equal to Is times Ns. Or the secondary current is equal to the primary current multiplied by the ratio of Np all over Ns. If Np, or the primary turns ratio, is 1, then Is is equal to Ip divided by Ns, the number of turns of the secondary. A current transformer differs from a voltage transformer in that the secondary current is determined entirely by the load on the primary system and not its own secondary load. In other words, the secondary current is determined by the current in the primary conductor. The voltage across the secondary load or burden will rise and fall depending on the current in the primary and secondary. Both the primary and secondary of CTs have relatively few turns of heavy wire and thus low impedance. Subsequently, a current is readily induced into the secondary portion of the primary current. As we have seen, CTs behave according to the mathematical relationship where Is is given by the turns ratio times Ip, and if the Np, or the primary turns, is 1, then Is equals Ip divided by the number of turns of the secondary. The transformer ratio of a CT is defined by the primary current divided by the secondary current. For a given CT, where the primary current is 100 amps and the secondary current is, say, 5 amps, then the transformer ratio or current ratio is 100 to 5, or 100 to 5 in this fashion. Or you could say it was 20 to 1. For the same CT, what would happen if the primary was looped back, then fed through the CT one more time? The CT would see a total of 100 times 2, or 200 amps, flowing in the primary. Therefore, the secondary would be 10 amps. The transformer ratio is 100 to 10, or 10 to 1. This is sometimes used if the primary current is too low for a meter to be able to read. You simply loop the primary conductor through another time, and you could actually loop it through a couple of times if you want, and that would increase the amount of current flowing in the primary that the CT would see. Looking at it another way, the CT sees two primary wires and sees a total of 200 amps flowing in the primary. Therefore, the secondary would be 10 amps. The transformer ratio then would be 100 to 10 or 10 to 1. Designating the polarity of a CT is very important, and it's usually done by the manufacturer to indicate um, the polarity of the secondary with respect to the polarity of the primary. And the primaries and secondaries are marked to indicate which direction the current will flow during each half cycle of current. So in this case, we've got a spot on the facing side of the CT, and we have a spot on the right-hand terminal of the secondary of that CT in this picture. The IEEE use a different standard, but it means the same thing. The spot side of the primary is H1 and the spot side of the secondary is X1. And in terms of the IEC, or International Electrotechnical Commission, they use P1 and S1 to designate the same thing as H1 and X1 that the IEEE do. Suffice it to say, we now have a terminal marked on the secondary, and we have a side of the CT marked with a spot of this particular donut CT. So what does this mean? This indicates that when the primary current is positive during the sinusoidal half cycle, or the current is flowing into the spot on the primary, the secondary current will be out of the spot on the secondary. Okay? So the primary current is positive during the sinusoidal half cycle, or current is flowing into the spot, then the current will be flowing out of the spot on the secondary. And what this also indicates is that when the primary current is negative during the sinusoidal half cycle, or the current is out of the polarity spot on the primary, the secondary current will be out of the non-polarity spot of the secondary. So the primary current is negative during the sinusoidal half cycle, current out of the polarity spot. The secondary current will be out of the non-polarity spot. This is sometimes shortened to primary current flowing into a spot results in secondary current flowing out of the spot. Potential transformers. In general, the secondary voltage is proportional to the ratio of the turns and opposite in phase to the primary voltage. This relationship is not completely exact for the following reasons. The exciting current that is necessary to magnetize the iron core causes an impedance drop in the primary winding. The load current that is drawn by the burden causes the impedance drop in both the primary and secondary windings. Both of these produce an overall voltage drop in the transformer and introduce errors in the ratio and phase angle. The net result is that the secondary voltage is slightly less than the ratio of the turns would indicate, and there's a slight difference in the phase relationship. These two errors are called ratio errors and phase angle errors, and may be represented by the transformer equivalent circuit. Now, I say this and I mention it, not that it's necessarily typical of only potential transformers. All transformers have these errors introduced into them because of nonlinearity and magnetization current. And so anytime you're using a transformer configuration, you should be looking at the exact transformer representation with all its losses. However, in most cases, you can ignore these losses when calculating the secondary voltage in terms of the primary voltage. I mention this only in passing so that it is in the back of our minds if we do get into very close measuring circuits, we have to take these into account. Okay. Designating the polarity of a PT is very important and done much the same as in the case of a current transformer or a CT. By marking the PT primary and secondary terminals and or indicating it on the nameplate. Again, this is especially important when PTs are used for relaying or revenue meters. As in the case of the CT polarity, the primary and secondary terminals are marked in such a way that when the primary current is positive during the sinusoidal half cycle, current into a polarity, the secondary current will be out of the polarity spot. Or in terms of voltage, voltage rise on the H1 terminal gives a voltage rise on the X1 terminal. On schematic drawings, PTs and CTs with their polarity markings may look something like this. This is an actual standard drawing using PTs and CTs with their polarity marks and connected to give the right measurements for a kilowatt-hour meter. You can see the PTs on the bottom left. The spot markings of the PT look like X's on the coils of the transformer, and in the case of the CTs, the spot markings look like square or rectangular boxes on the sides that are the marked sides of the CT. This is another example, this time on a protection circuit for a transformer differential protection circuit. You can see that the markings for the PTs and the CTs are designated with circles, and in the case of the actual power transformer itself, the polarity markings are indicated in the same manner. This is the end of Chapter 3.